What we're going to do now is talk about energy levels for electrons. So earlier, we talked about atomic theory and atomic structure, and it gave you a pretty good picture of what an atom looks like. And it mentioned that these electrons live on the outside, but I didn't really give you a good description of these electron clouds and exactly where the electrons reside. So that's what we're going to do here. So historically, there were some interesting experiments that were done to kind of probe what was going on inside of an atom. In the very early days, they had experiments with cuvettes. And so a cuvette is nothing more than a piece of glass about yay big that would be filled with a sample, and you can fill this with whatever you want. And what they expected to happen was that when light would hit the sample, if they use white light, for example, that has all of these different wavelengths of light in it, then all of these different wavelengths of light would be absorbed. And when they would come off, all the different wavelengths of light would be emitted, and you would see this beautiful rainbow, like you see here on top. But what they actually observed was something very different. Different elements would give them different, what are called absorption spectra, different lines or different peaks in the graph. So for example, for sodium, there were a bunch of lines, some that were yellow, some that were orange, some that were light blue. Hydrogen gave them purple and orange. And basically every element in the periodic table that they had tested gave them different patterns, both in terms of how many lines there were and the spacings between the lines and the colors of the lines. And they couldn't really explain or justify why they were getting all of these different patterns. It didn't really make sense with the physics and the science that they understood at the time. Okay, and so a person named Joseph Balmer came up with an equation that was able to predict the positions of the lines for hydrogen. So he worked on hydrogen atom line spectra. And this was done in the late 1800s. And he had an equation that he had used to predict what's going on. And it seemed to work, but he really had no idea why it worked the way that it did. Okay, and so it took a little bit of time later for people to discover what was going on. Okay, so let me tell you a little bit more about what was going on. So the first person on the scene to really come up with a great idea for this was Max Planck. And so Planck had this crazy idea that maybe energy should be quantized, meaning that only certain energy values are allowed, or only certain energy levels are allowed. And the way that he expressed this was that the energy should be directly proportional to the frequency. Okay? And this makes sense if you think about it. Okay, I'm going to use my hand as a visual aid. Okay, let's pretend that my hand is a wave. Okay, so here's a nice slow wave. Okay, relatively low frequency. And here's another wave, higher, faster frequency. Okay, which one do you think has the greater energy? First one or the second one? Okay, probably the second one, you would say. So Planck proposed that the energy should be directly proportional to the frequency. And the constant of proportionality is something called Planck's constant, which is given the symbol h. And the numerical value for h is 6.626 times 10 to the negative 34 joules times seconds. So now, once Planck came on the scene, a bunch of other scientists further developed this theory called quantum theory. Namely, somebody named Niels Bohr was very prominent. Okay, and so Bohr was responsible for what is called old quantum mechanics. Old meaning that it was pretty much put forth about 100 years ago. Okay, and so in 1913 or so, Bohr assumed that energies in an atom were directly related to angular momentum. Angular momentum has to do with things going around in circles and how fast they're turning around. Okay, and so Bohr assumed that these orbits, or these angular momentum, were quantized. And he came up with a model very similar to a planetary model that had been done years and years and years ago to describe how the planets orbit the sun. And people liked his ideas because it kind of made sense, or at least it reminded them of some other experiments that were done earlier by other people, or some other models that were done earlier by other people to describe things like planets and orbits. Okay, and so here's Bohr's explanation for what's going on in these atoms that have these electrons that are in these energy levels. Okay, Bohr said that you have these atoms that are in these different orbits or energy levels, and when they get excited with light, they absorb that energy, and so they go up to a higher energy level. Okay, but that is kind of temporary, right? They got excited, and now they want to come back down. And so when they come back down, they release the energy to a lower energy level. And what he kind of figured out was that because the energy levels themselves are fixed, right? You can only go from here to here, or here to here, or here to here, or here to here. Only certain levels are present. That means that the gap between those energy levels is also fixed, which means that the energy difference between these levels is fixed, which also means that the frequency is fixed, or the wavelength is fixed. Bottom line, only certain colors are going to be observed because those colors are related to what the difference in energy was between these energy levels. Okay, and so Bohr came up with a pretty good explanation for what Balmer and other people had observed in the atomic line spectra. Okay, these lines in the atomic line spectra were due to emission or absorption of specific wavelengths of light by these electrons in the atoms. Okay, so then after Bohr, a bunch of other people came on the scene, and they came up with what's called new or modern quantum mechanics. Okay, so let me try to describe to you what was going on. Okay, they came up with rules for quantum numbers. And the idea was Bohr's model was very, very good. Okay, it was able to describe everything that needed to be done for the data for hydrogen. Okay, but what I'm going to show you now is the good, the bad, and the ugly. Okay, the kind of truth about what was going on and why it didn't really work for anything other than the hydrogen atom. Here's the good news. Bohr was able to come up with a model for the different energy levels in the hydrogen atom, and it explained everything that Balmer had observed experimentally. Okay, so that's great. Okay. Here's the bad news. It only worked for hydrogen, or perhaps more specifically, things with only one electron in them, which are called one-electron systems. So that was really bad. Okay. You wanted something that would describe not just hydrogen, but all of the other elements in the periodic table. And it just didn't seem to work for anything other than hydrogen. And then people figured out the ugly truth that even if you had wanted to come up with some equation or some model to perfectly describe what's going on, it's impossible, right? The mathematics kind of proved that you could not do it, okay? There really wasn't any way to solve the equations that were necessary to describe the energies and the electron energy levels in anything other than something with one electron in it. Okay, so what did people do? They worked and they worked and they worked and they worked, and they figured out why all of these problems existed and some other, I guess, workarounds or solutions to the problems. Okay, so what I'm going to do now is show you how Bohr's theories got modified to what we currently use to describe atoms, and more specifically the electrons in the atoms. Okay, so Bohr had come up with these energy levels, which were described by a principal quantum number, which we use the letter n to describe. Okay, the reason that Bohr's model failed wasn't that it was too crazy, but that it wasn't crazy enough. Okay, people had a little bit of a problem understanding this whole quantization of energy. That seemed kind of weird to them. But what further people had discovered, like Schrödinger and Heisenberg and Pauli and Dirac and a bunch of other scientists, is, you know, Bohr was actually onto something, but he didn't go far enough. Okay, Bohr had assumed that only one thing was quantized, but there are actually 4 different things that are quantized. And these are the 4 different quantum numbers in an atom. Okay, and so the first one is called a principal quantum number, and this is given the letter n. This is exactly the same as Bohr's energy levels, and n is any natural number. So it could be 1 or 2 or 3, anything like that. This basically tells you what shell or what energy level the electron is in. Okay. The second one, which was kind of new, that Bohr did not really describe so well, is the angular momentum quantum number, which is given the symbol L. Okay, and so the thing is that L actually depends on n. Okay, L has to be less than or equal to n minus 1. And so L is what we now call an orbital. Okay, so for example, if L is equal to 0, this is what we call an s orbital. Or if L is equal to 1, this is what we call a p orbital. If L equals 2, this is a d orbital. And if L equals 3, this is an f orbital. There actually are other orbitals after f, like g and h, and they just go in order, alphabetical order. But nothing that you find in the periodic table actually has these things present, so we don't really worry about them. Okay. The other name for an orbital, by the way, is a subshell. In other words, if you zoom in to these energy levels where the electrons are, you get really, really close. Even if you're in, for example, the second energy level, there might be little sublevels within there. And so one of them might be the s orbital, and the other one is called the p orbital. The third quantum number is called the magnetic quantum number, which, depending on the book you use, might be either called m or m sub l. And there's another rule for determining the value for this. So the qualification here is that the absolute value of m sub l has to be less than or equal to l, which means that m sub l itself could be a negative number. Okay. The physical significance for this magnetic quantum number is that it tells you spatial orientation and degeneracy over the orbitals. So spatial orientation means where in space is it located, right? Is it moving around the x-axis or the y-axis or the z-axis or in between these axes? Okay. Degeneracy might sound like some dirty old man looking at naughty pictures or something, but that's not what we're talking about here. Okay. Degeneracy means how many different ways can you have the same exact energy. Okay. So equal energy, but different orientations. Okay. So for example, if you look at something like the p orbitals, okay, or the p subshell, L is equal to 1, but m sub L could be either 1 or negative 1 or 0. Okay, so there's 3 different values for m sub L, which means that the degeneracy of the p orbital is threefold. There are 3 different p orbitals that have exactly the same energy. Sometimes they get called px, py, pz to try to orient them along axes so that you can see them a little bit better in 3D space. Okay. The fourth quantum number is something called the spin quantum number, okay, m sub s. And what the spin quantum number tells you is something completely unrelated to the other 3. Okay, so spin is weird in the sense that it has no relation whatsoever to either n or l or m sub l. Okay, it's completely separate, and it's actually not related to spatial coordinates at all. Okay. It has more to do with what's called the spin coordinate. There isn't really a classical way to describe this, but it's kind of similar to angular momentum. Okay. The other weird thing about spin is that the values for the spin quantum number are not even integers, right? For everything else, we had whole numbers, like 1 or 2 or 3 or 0. Spin is a half integer. So you can have a spin of positive 1/2, or you can have a spin of negative 1/2. Okay. The easier spin is called spin up if it's plus 1/2, spin down if it's negative 1/2. This has to do, or we associate it with how the electron is spinning around, but it's not a real spin like rotating like this, but more about how it orients itself in relation to an external magnetic or electric field. Okay, and so what I'm going to do now is show you a picture of what these orbitals might look like, so you can kind of get a feel for what all of this theory kind of tells us. Okay, so over here are depictions of different orbitals. The top one is an s orbital, which you can see looks pretty much just like a ball or a sphere. And so again, this would be L equals 0. This one here is a p orbital or p subshell. This would be L equals 1. And you can see that there are 3 different p orbitals, right? What we call px, pz, and py. And then down here are the d's. This is where L equals 2. There are 5 of these, okay? And I'm not going to read them all to you, but they have different orientations along different planes, either xy plane or xz plane or yz plane. And then down here on the bottom are some crazy looking f orbitals. L equals 3, okay? And there are actually 7 of these. So there's an interesting pattern, right? There's 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals.